morning, everybody. I'm Usama, and I'm going to talk about a very interesting domain which is called as confidential computing. And this very much relates to the OCP initiatives in terms of attestation. And that's what we have seen, that attestation is mostly misunderstood by different people, so we wanted to systemize the knowledge that exists in this domain. And this talk is basically going to exactly present that, how different things fit together, and how should one think about attestation for confidential computing use cases. And this is joint work with industry experts from ARM, Thomas Fossati and Simon Frost, that I have worked with. And I have designed the outline as follows, which is that I will first state what the problem statement is, what were we focusing on, and then our approach, and then I will talk about the specific contributions that we have made over the state of the art, and finally summarize the talk. Okay, so attestation in confidential computing. Firstly, maybe just an overview of confidential computing. The idea here is that I as the relying party, as it's called in the RATS standard, which is someone who is the workload developer, let's say. He wants to run some application on the cloud, but the trust model is very strong that we do not want to trust the cloud service provider. Under this trust model, how do I still provide the security guarantees that my workload, my data is still protected? And that's what the whole stack here is called as the attester, which consists of the hardware, software, and firmware, all the layers of the stack. And the process of attestation basically works like this, that I have this attestation request, which the relying party sends over to the attester that's in the cloud. And the attester generates an evidence, which is the set of claims that it sends back to the relying party in order to appraise it. And based on that appraisal, if that appraisal succeeds, it's going to send the data and the secrets over to the cloud. So the secrets and the data which are to be protected are sent only if the appraisal of the evidence succeeds. So this is just a high-level idea of the thing. If you are not familiar with attestation at all, just think of it as a border control pass that somebody is going to pass through. What we do is we prove our identity that, hey, I'm this guy, and this is my passport, this is my visa, and then the officer, visa officer, the border control officer basically evaluates, scans your passport that this is legitimate, it's not forged, and so on. And then he checks your visa that it was issued by, the passport of course was issued by some governing authority which he trusts. And the visa was also issued by some authority which he trusts. So this is the kind of checks that the visa officer there is performing in order to allow that person to pass through the gate or not, or pass the border control or not. So just a high-level idea in case you are not familiar with what this is all about. The problem statement. So what specifically we see in the state of the art is that there is an attestation architecture, but it's not TE-agnostic, which means that trusted execution environments, different execution environments now exist, but the architecture itself is not, from the attestation perspective, it's not TE-agnostic. I mean, you cannot have any TEE and then evaluate the evidence claims and so on based on that architecture. I will explain a little bit of details as we come near to that point. The second thing, the second problem basically is that there are no mappings to that, no clear mappings to that attestation architecture. Although one attestation architecture standard, RAT standard exists, but there are no clear defined mappings to that attestation architecture. And the third one is that there is something called as formal verification, which is the mathematical way of evaluation of the properties of the system to provide more guarantees on the system. And that's what something is non-existing at the moment. There are no formal specifications of the attestation mechanism at the moment for any trusted execution environments. So our approach was basically to how to deal with these three specific problems that I have just mentioned. And the idea basically, sometimes it works too fast. Okay, so the approach was like this, that we want to have, as I said, like the systemization of knowledge. So we wanted to have some categorization of, or a way of thinking about all the systems that use attestation. And the thing that we came up was that we have attestation lead solution, architecture lead solutions, sorry, where we have the category which provides the kind of specifications on the basis of which one can build its own platform, right? So I'm not yet happy with the terms. Of course, one can debate on that, okay, so these solutions also use architecture leads as the starting point, but I mean, from the examples, it might be more clear that this ARM and RISC-V are in this category. They provide you the specifications on the basis of which one can build, a third party can build its own implementation. And on the other category, there is this vendor solutions, which is a complete product. So the platform details have all been established, right? And of course, on this side also there are specification from the perspective of that they are also vendors, but as I said, like the terminology we are not yet fully happy with, but there is a clear distinction between the two categories, which is the level of customization possible. On this side, it's a lot of customization. You can build implementation based on the specifications. You are very free to still satisfy the specifications and build different products based on that. On this category, in this category, you do not have many flexibility. The platform details are all set. Although people are wishing to have some flexibility also here, there is Intel ongoing discussions on inside Intel about this. And on top of either of these solutions, one can build complete frameworks, which means that basically you provide to the user in one line, let's say, everything that he needs to do to do the appraisal. So it's complete solution which is built on top of either the architecture lead solutions or the vendor solutions or a combination of these two solutions. So this is what we call as the framework. So it uses the underlying solutions as the basis and builds the verification on top of that. So what we did was we basically took ARM CCA from this architecture lead solutions as an example of this category. We took the Intel TDX, which is the upcoming solution of Intel, the follow-up of Intel SGX, which is supposed to be announced, supposed to be released for public review next year. And in the category of frameworks, we have our own framework, which is called as SCONE, which is what we consider. There are others, Grameen, Microsoft Azure, Attestation, and Verizon, and so on. So this is the overall categorization that we did. We selected one solution. We provided complete specifications that I will talk about. All right, so overview of the approach. On the left side are the blocks that we have just seen. Architecture lead solutions, ARM CCA, I just talked about. Vendor solutions, Intel TDX that we selected. In the frameworks, we selected SCONE. So any of these three solutions can be sent as an input to this block, which is the TE-agnostic attestation architecture-based specifications. In short, like what this exactly means is that we have an architecture-based specifications, which are not written in natural language, English, for example, which can be misinterpreted, which are rather represented as specifications in three different categories, which is the provisioning stage, let's say, when the platform is provisioned with a secret, then to the initialization when the platform is booted, and then in the runtime when attestation protocol is done on the request on the first slide, which I showed that there is a request and then there is an evidence. So the actual attestation protocol. So we think of it in terms of these three processes for any attestation, any trusted execution environment. And now when we have these kind of specifications which are TE agnostic, taking any trusted execution environment from either of these two categories or taking a complete framework, we can then build these specifications, and now they are still not formal. So we need to convert them to the formal specifications, which means that they are represented in mathematical formulas, and then one can do a formal analysis, which means a mathematical analysis, prove some properties, provide some security guarantees, and have some stronger assurances on the system. And what does this consist of? This basically consists of transforming these specifications to the formal model, which will be in a specified language with well-known semantics and syntax. And it will also use some assumptions because, of course, we cannot model everything. We have to make some assumptions in order to deal with the system to verify these properties. And it's one of the strengths of this, that it reveals the assumptions that were used to prove the system, so that the properties hold only if these assumptions are correct. If any of these assumptions are broken in the implementation, the properties do not hold anymore. And then these properties, which I already talked about, let's say from attestation perspective, integrity, for example, and the confidentiality of the secret are the most important properties. Out of all of this, starting with any architecture lead solution, vendor solution, or framework, what we get as an output is a formal proof that the system properties hold for this specific model under these specific assumptions. So this is the overall idea of the approach. And there are specific contributions which are parts of the approach itself, and the ones that I introduced in the problem statement. I will now talk about each of them. The first one, TE-agnostic architecture. I introduced in the beginning that there exists a standard which is called as RATS, Remote Attestation Procedures. And this is already an RFC 9334. However, there are limitations of this standard, which are namely, the first one, it cannot express anonymous attestation precisely. What this means is that if I have mechanisms such as Intel's APID, Enhanced Privacy Identification, I cannot precisely represent this in terms of this standard. Secondly, there is, in terms of remote attestation, there are specific trusted execution environments such as Intel SGX and Intel TDX, which have local attestation as an essential part of the remote attestation. So you cannot essentially do remote attestation without having done the local attestation first. And the standard, unfortunately, does not represent or considers the local attestation as out of scope of the standard. So this is really not, these problems really lead to the real world trusted execution environments not being representable in this standard. And we have already done a thorough analysis of the standard and submitted an errata to the RATS working group, and we are actively working with the working group to resolve these. And what we have come up with is our proposed architecture is like this, which is TE agnostic. Basically, the changes that we make to the existing architecture is basically, first of all, we add another role to the architecture, which is this identity supplier, which is provisioning an identity, a cryptographic identity to the attester, and it can be static or it can be dynamic. So it basically takes care of the provisioning step that I showed in the approach. So this part basically comes from the RATS architecture itself. And by adding this role, basically we take care of the anonymous attestation. The second limitation that I mentioned, that the local attestation, so now with this role, sorry, before I go to local attestation, with this role basically and this artifact, basically now we can take care of Intel's APID attestation mechanism. And on the other hand, now talking about local attestation, we enhance the terminology of RATS standard by differentiating local versus remote. So whatever artifact appears here, the evidence, for example, can be local, and remote we add prefixes local, evidence, remote evidence to distinguish between local and remote. And hence now we can take care of Intel TDX, Intel SCX attestation mechanisms. We also add the attestation request and attestation challenge as part of the artifacts to the standard. Now, talking about the state of the art which exists in this domain. So there are three main works which IETF RATS working group, which I have already described. They have the standard 9334. And then there is an academic effort, Manithre et al. And then there are industrial effort from Nimi et al. From Huawei. So the first one, for example, let's talk about the architecture. So it's this architecture, IETF RATS, was co-developed with DICE. And this one uses the RATS architecture itself. And Nimi et al. Basically adapted the RATS architecture. And now I will define the three groups that I described in the motivation that we had in the systemization. And the first group basically is the vendor solutions. The RATS working group does not provide any mapping at all. And the second one, this academic effort, they provide the mappings for SCX and others, but unfortunately the mapping for SCX is inaccurate. And this last work also has very high level mapping of SCX. In the second group, which was modifiable architectures, or you can build products on basis of that architectures, ARM and RISC-V. In that category, there is only this work which describes a high-level summary for ARM CCA. And finally, in the group of the frameworks, there is no existing work at all which describes or which presents a mapping to the architecture. So here is our novel contribution for the frameworks. Okay, so what does a mapping look like? Specifically for the category of ARM CCA, we have different target environments and attesting environments. And before I go to that, let's say at a high level, there are two attesters which are composed together, and that's why it's a composite attester. We have a platform attester, and we have a realm attester. The platform attester has this attesting environment HES, and the target environment monitor security domain. And in the brackets, you see different claims which are used for that evidence. For example, the system boot state, the CCA parameters, security lifecycle that should always be secured, that the verifier should always check, and the hash of the public key RAK, which basically is this key of RMM. And this binding between the two keys is basically the important bit, which is preserving this relationship. So the platform evidence consisting of these claims is basically sent to the RMM, which is the attesting environment for RAM attester. And it measures, and its target environment is basically the RAM instance. And it has initial measurements and the extended measurements, which are realm initial measurement, RIM, and REM extended measurements. And the composite evidence will be sent over to the verifier for appraisal, which is composing of remote this platform evidence and the realm evidence. Now I want to talk quickly about the formal specifications. How did we develop the formal specifications, mapping this to the architecture, to this trusted execution environment agnostic architecture? Now we have, for the formal mappings, we actually need a specific protocol in a formal language. And that's something like this. We have the testing environment for the attestation protocol of ARM CCA. What we do here is we represent all of this protocol in ProVerif, which is a language with well-known semantics and syntax, and that can then evaluate the formal properties of the system. And what does the formal analysis look like? We have, as I said, we have a formal model, we have assumptions, and then we have properties. The assumptions are that the verifier has pre-configured public key of the platform attester for signature verification, and a channel between the HES and RMM is assumed to be secure. So these are the two assumptions which the proof is based on. And these assumptions are important, as I said, that this helps us evaluate that these assumptions should always be preserved. If they are not preserved, then the property does not exist. Property does not is not valid. Okay, the properties that we proved were the integrity of the platform evidence and the RAM evidence. And the way it works is that we have a data and events. So two events are described. These are the accepted and the sent. When the sender sends the message with the specific claim that is represented here as data, and at the end when it's accepted by the verifier, the two things should be the same. The claims should remain the same. There should be no interjection by a man in the middle by changing that data. So the data integrity is preserved. So this is the high-level bit which this property is preserving, that the data from the sending point up to the ending point is preserved with freshness, which is due to these injective events in ProVerif. Right, so these were the three main contributions that the work was focusing on. Other than that, I just want to quickly describe about the security and the design issues that we also found inside that. In the TDX part, where I just talked about that in the vendor solutions part, we have this. Intel actually claimed that this is the TCB of the TDX from Intel TDX white paper. And we transformed it to a standard way in which one can understand that. So everyone in the room hopefully can understand that this is the certificate chain, this is the root certificate, root CA, this is the end entity, and this is the certificate corresponding to that entity, and so on. So there is this chain of trust starting from the root cert up to the end entity. However, not all of the certificates are standard. Here there are X509 standard certificates, but at the end, Intel uses basically customized format certificates like structures. And this TD code, even its structure was not clear. We informed Intel about all of these missing details, but the high-level bit that I want to focus here is basically that Intel claimed that this is all that a TD needs to trust, and all other software is untrusted by the trust domain. And this really was wrong, because if we focus here, this TD is what is trusting is here. The TD quoting enclave is abbreviated here as TDQE, and it's not possible that the chain above can be untrusted, because it says that all other software, which includes the provisioning certification enclave, PCE, is untrusted, which is not possible, of course, that we cannot have an entity not trusting the chain above. And then we reported it to Intel, and it was fixed, and now this TD quoting enclave is replaced by the TD attestation software in the latest version of the Intel specifications. And quickly about SCOAN, in the frameworks category, basically there are a lot of details here, but let's just focus on one specific problem that we found. So there is local attestation versus remote attestation. And what does this mean is that if two entities, that is the attester and the verifier, are on the same platform, they can simply do local attestation. And the SCOAN design was actually using remote attestation even when the attester and verifier were on the same platform. The loss here is in the performance. This is not a security issue, but there is a performance issue, because there are a number of verifications that one has to do. And then the local attestation uses, so the local attestation uses MAC rather than the signatures, which are expensive, so it leads to a boost in the performance. So I just want to quickly summarize with the challenges first. There are like 1,500 pages of the specifications of TDX at the moment. It's not yet complete. It's still in work in progress. And other than that, it inherits specifications from SGX, which is currently used as its base, which has its software development manual alone is of 5,000 pages. And the specifications are given in the natural language, which are object to different interpretations. In the frameworks category, SCOAN closed source nature was the biggest challenge that we had to face. Okay, the summary or the take home from this is that we have a TE-agnostic approach which does comprehensive specifications based on the TEE-agnostic architecture that we propose, and the formal analysis, and the combination of two things is the most powerful thing that our approach provides, and none of the approaches currently do provide that. For TDX, as we have seen, how do we express precisely the trust boundaries? It's very important. And in the future, we are moving towards a TEE-agnostic verification infrastructure where we verify the whole stack starting from the bottom up to the top for transparency and interoperability between the trusted execution environments. And what this mean is basically that we integrate the attestation protocol with TLS, which is the remote attestation TLS. We want to verify that. And the integration of the attestation protocol with the VTPM, the virtual TPM. So then it can provide basically the interoperability. And the call to action, basically, I would like to invite you to all to specify your protocols using this architecture and the proposed formalism. That is this approach, which is powerful and can lead to disclosure of your of many issues in the design. And additional information is available here at this draft, which we will update in a few days. We have an updated version. And I'm very happy to take now questions or have discussions around the topics that are of interest to you. Please.
I'm curious how you decided on ProVerif. I've seen a few options.
Yeah, sure. So yeah, there are some tools like Tamarind Prover, which also do it. So our goal basically was to deal with it at the symbolic level. Start from the symbolic level, and then one can go to the computational. There are other tools available. Inside the symbolic one, as I said, Tamarind and other tools are also available. Our choice was motivated by our previous analysis, which I did before, was also based on ProVerif, and that's why I used ProVerif. In terms of, from technical point of view, ProVerif is much faster than Tamarind Prover, and it provides more automation. These were the two motivating points for us to use ProVerif first. At the moment, there is also there is this SEPIC tool which has been developed, which interrelates the two tools. So one can actually transform ProVerif model to Tamarind, and now it's possible, which is due to the S&P, I think, last year work which was presented there. So it's possible to translate our ProVerif model to Tamarind and interchangeably. So there is no issue in doing that. Any other questions, thoughts, comments? Okay, then great. Then I would be very happy to take any discussions offline, or if you have any system that you would like to discuss or something that we can formalize from OCP perspective using this approach, I would be very happy to discuss. Thanks a lot.